Hi, everyone. Welcome. We're just going to give a couple of minutes for folks to trickle into the webinar before we get started. Hi, folks. Welcome. Just giving a couple of minutes more as folks are still trickling in, and then we'll get started. All right, let's get started. Hi, everyone. Welcome to RMI's workshop titled Low Embodied Carbon Concrete, Near Zero and Zero Emissions Concrete for State DOTs. If you are joining us for the first time, we wanted to make you aware that we've been doing a workshop series for the past year. We've covered 3 topics previously, and this is our 4th session. Our first workshop was an introduction to Buy Clean and EPD program implementation, which was last year. We also had a session focused on limestone calcined clay cement, which is an emerging blended cement product. And earlier this year, we had a session that did a deep dive on specifications and provided some guidance on how to move towards performance-based specifications for DOTs. So those resources are available on our website, both recordings and slide decks, which we can share as a follow-up to this webinar if you all haven't seen those resources. Today, we're going to be focused on near zero and zero emissions concrete. So this is an emerging area of interest for infrastructure builders, for the building industry, as well as we seek to move towards lower embodied carbon materials. And near zero and zero emissions concrete really provide an opportunity for us to eliminate the emissions associated with cement and concrete. Go to the next slide. Today, I'm joined by a few esteemed speakers who will walk us through this topic. My name is Anish Tulak. I'm a manager in the Carbon-Free Buildings program at RMI. I'm joined by my colleague, Ben Skinner, who is part of our Climate Aligned Industries program, and specifically our cement and concrete focused initiatives targeting the industrial side of this issue. And we're also joined by Sabbie Miller, who is a professor in the Department of Civil and Environmental Engineering at UC Davis. And Sabbie leads the Green Engineered Materials and Systems Research Group there. And I'm excited to hear more about her work today. And she will be kicking off our presentation. So if we go to the next slide, here is an agenda for the meeting. We'll hear from our speakers for about 30 to 35 minutes. We'll hold our live Q&A until after both speakers. Of course, throughout the presentation, if you have questions, feel free to use the Q&A feature in Zoom, and we'll provide text responses when appropriate or hold the more detailed questions for that live Q&A portion after the presentations. And then we'll end the webinar today in a live polling session where we aim to hear from you and get a sense of what resources you would need to move this issue forward in your role today. So with that, I will pass it off to Sabbie to introduce us to this topic of near zero cement and concrete.
Thanks so much, Nish, for the introduction and for inviting me to give a talk. If I could trouble you to click on the next slide. So what I'm going to do today is give kind of a high-level context, just in case this is a new topic for you. Although assuming that many folks on the call are deeply immersed in the carbon dioxide emissions world and understand the nuances associated with cement production and concrete production, we won't go into that into too much detail. Then I will go over some background on different types of alternative materials that you might start to come across in DOTs, as well as give some steps to start to integrate some of those new technology strategies. And then at the very end, I'll give a list of fast wins and how we could start to approach reducing greenhouse gas emissions quickly, even when we can't necessarily introduce one of the new technologies as fast as we would like. So with that, awesome. All right, so again, super high level. When we produce our cementitious materials, particularly our Portland cement, we end up emitting a fair bit of greenhouse gas emissions. Actually, relative to other materials, cement is pretty low emissions. And then when you take into account that cement is just one constituent in concrete, concrete is really low emissions per kilogram of material or per cubic meter of material. But we use a lot of cement and concrete. And the way that we're producing our cement requires limestone decarbonation, otherwise referred to as calcination. Basically, you're taking your calcium carbonate, you're going to have some off-gassing of carbon dioxide to get that reactive calcium out. And then you're going to form calcium silicates, which facilitate our calcium silicate hydroxide systems, which actually allow for the formation of concrete that has nice rigidity, strength, durability characteristics, et cetera. That temperature that we need to form those calcium silicates is even higher than what we need to do limestone decarbonation. So now we have a high temperature industrial process, which by and large, we're still using fossil fuels for. So what we end up seeing is both mineral-derived CO2 emissions from the decarbonation of the limestone, plus emissions from those fossil fuels that are leading to the emissions for our cement. If I could trouble you to click on the next slide. So while cement is just one constituent within concrete, it actually is the largest contributor to the carbon dioxide emissions for concrete. So by volume, our concrete is predominantly aggregates, but aggregates don't tend to have very high emissions. So a lot of the strategies that you're going to see to hit net zero are actually tackling the cement within that material. Now, keeping in mind that the cement is necessary to actually achieve a lot of the performance characteristics we want out of our concrete, when we look at these alternatives, we need to pay attention to not only are we reducing emissions, which we do need to check, but also are we getting the correct performance out of this material? Is it something that we want to use in a specific application versus another, et cetera? If I could trouble you to click on the next slide. All right, so a couple of cool alternatives that are coming up in terms of what we could replace our conventional Portland cement with. Among the ones that you're going to see a lot of are blended cements. Portland limestone cement is probably already being used in your area. This is a form of a blended cement. Basically, you've got a fair bit of clinker, usually about 15% of that clinker, maybe a little bit less depending on your cement producers, is going to be replaced with an interground limestone. And then you've got about that 5% gypsum just for setting control. Other types of blended cements that you might come across include ternary blended cements. These oftentimes are leveraging still some of that limestone filler that you're going to have for your Portland limestone cement, but also a pozzolan. And there's actually been some studies that have shown there's a beneficial interaction between the interground limestone and our pozzolans that could lead to very similar mechanical performance out of our concrete, great durability characteristics, but possibly slightly different workability conditions. So what we're looking at when we're looking at a blended cement and a ternary cement is you're probably going to get really similar performance, maybe even better performance, but you might need to do a little bit of education of the construction workforce to make sure they feel comfortable actually placing the material. Now, as we think about what we're adding to our blended cements, we also start to come across the discussion of supplementary cementitious materials. Now, by and large, in the US, we're adding our supplementary cementitious materials at the concrete batching phase, not at that blended cement phase where we're actually intergrinding with our cement product. But you can see these showing up in both locations. For the vast majority of our supplementary cementitious materials, you end up with relatively similar performance, whether you blend it in at the cement stage or blend it in at the concrete batching stage. Some of the materials that are going to be studied in this area that you're going to see more of include other coal combustion products beyond fly ash. We're pretty big fans of fly ash already, but there's things like bottom ash that are going to be starting to kind of come up a little bit more in discussion. Other types of slag. So we already use a heck of a lot of blast furnace slag, but there's other types of slags associated with different metallurgical processes, including things like ladle slags that look like they could have desirable reactivity, a variety of different types of natural pozzolans. Interestingly enough, calcined clays are lumped into the natural pozzolans category. So the LC3 that was mentioned earlier falls into this category. Other types of natural pozzolans that you might come across include things like volcanic resources like tuffs and zeolites. We also end up seeing that diatomaceous earth falls into that category. And then there's a bunch of other types of SCM. So you might see agricultural ashes, et cetera. All of these, when we're looking at them, they might have different technology readiness levels. They might have slightly different levels of variability in terms of their composition. And they also might have differences in terms of where they're located. So do we have a natural deposit of this resource? Do we have a local farm that's producing the agricultural resource that we could turn into an ash? So depending on your location, you might have access to different resources for those supplementary cementitious materials, but the US in general has access to a bunch of these resources. Next. What we end up seeing, particularly with our biomass resources, is there's a lot of research going into, wait a minute, if it's biomass, that means that it underwent photosynthesis, and that means that we could potentially store atmospheric CO2 in what is basically our most consumed building material, right? Our concrete. So if we could take atmospheric CO2 and stick it in our concrete, can we turn our concrete into a sequestration mechanism? So with those biomass resources, what you're going to end up seeing is ashes from things like the farming practices that we have. So waste residues, not food products, but basically things like leftover hulls and shells. How can we start to use those as ashes, as well as how can we start to use those as biochars? Those chars tend to be a little bit more stable than biomass in general. And if ground properly, there's some pretty good research that's suggesting you might get desirable characteristics out of your concrete system. And then you're storing a little bit of carbon in your concrete. It will change the pigment of your concrete a bit. You'll end up with slightly darker concrete. On that same topic, though, the idea of storing carbon dioxide in our cement-based materials has also been approached from a carbon mineralization standpoint. So not just biogenic carbon with our bioashes and our biochars, but also what if we can accelerate how quickly concrete carbonates? It's going to carbonate anyway, assuming appropriate exposure conditions. How can we actually make that happen a little bit faster? Will there be any deleterious effects if we have things like steel reinforcement in there and we just plummeted the pH of the system? Or if we don't have any steel reinforcement, are there going to be any other impacts that we're concerned about, like the change in porosity that we end up seeing from those carbon mineralized products? There's a bunch of different approaches that have been explored. Many are focused on mineralizing the cement itself, whether that be using a clinker that can actually carbonate, or whether that be integrating a certain amount of carbon dioxide to that hydration product through a carbonation process. We also are seeing this a little bit in the aggregate space, basically trying to form aggregates, which are by and large the predominant constituent they're putting into concrete. Sorry, I stuttered over that. But actually making that something that is carbon mineralized. Next bullet point. Now that kind of leads us into these alternative clinkers. So I just mentioned that some of these cements that folks are looking at can actually carbonate instead of hydrate. Hydrated Portland cement has the ability to carbonate, but there's also a few classes of cements that can actually solidify through reactions with carbon dioxide. These include things like carbonatable calcium silicates, as well as our magnesium oxide-based cements. What turns out to be the case is at the moment, the way we're engineering these clinkers, we still actually need to undergo a kilning to a certain extent. If we use magnesium carbonate to form a magnesium oxide cement, we actually end up with higher CO2 emissions than just our regular Portland cement. However, if we could use magnesium silicate, then we're a little bit better off. However, these cements, if we're able to put them in concentrated CO2, they could solidify with that reaction with carbon dioxide, as opposed to with a reaction with water. As you can imagine, you're talking about a different pH of your system again, as well as some different performances. but you are holding on to some carbon dioxide. And if you're able to capture that carbon dioxide from, let's say, a flue from an industrial process, then maybe you're utilizing carbon dioxide that would have otherwise been emitted. Other types of alternative clinkers are actually ones you've probably already come across, such as our calcium sulfoaluminate cements, which I realize have a very sordid history, but because they set so quickly, they still show up a fair bit in our transportation applications. Those types of alternative clinkers actually have lower greenhouse gas emissions than our conventional Portland clinker because the mineral phases that are present don't require as much calcium, so there's less limestone decarbonation, and the mineral phases can be formed with a lower enthalpy of formation, so there's actually less energy that is necessary to hit the correct stages for the kiln. Other types of alternative clinkers include ones that, again, are magnesium-based. You've also got your belite, yeelimite, ferrite type cements. All of those, again, we're oftentimes trying to look at them to see if we could reduce energy demands and reduce the demand on calcium such that we could lower the carbon dioxide emissions. Next bullet point. Other types of alternative cements that you might come across include ones that don't even require clinkering. We don't have to send them through a kiln. These include things like our alkali activated cements. Alkali activated cements are basically cements that are able to form hydrate mineral phases through use of solid precursors, by and large aluminosilicates, and an alkali activator, usually a dilute solution that's based on a sodium or potassium-based alkali. What we end up seeing for these types of cements is that there's some differences in constructability. So you might end up seeing like slightly faster set times, which could be awesome if you want to get folks on your roadway quickly. It also means that you need to be a little strategic and make sure you place the material at an appropriate time and it doesn't get stuck in the equipment on the way there. In addition to that, as you can guess from the name alkali, these have pretty high pH and they do require slightly different handling just because you don't want folks to get exposed to those higher pH systems. Next slide. In addition to this, we actually have a whole bunch of folks that are looking at completely different ways of synthesizing the raw minerals that we need in our Portland cement. These include things like electrochemical production pathways as opposed to leveraging thermal kilns. We also have folks that are looking into biocements. There's a couple of different classes of biocements, but the most predominant ones that are showing up are using either bacteria or algae to form the calcium minerals, as opposed to using limestone, which has basically absorbed carbon dioxide through a weathering process that took centuries and millennia. They're using algae and bacteria to do it much more quickly, so that when you do emit the carbon dioxide from the Portland cement production, you're emitting carbon dioxide that you also recently had absorbed from the atmosphere. So they're hoping for a little bit more of a circular action on that. There's also a few folks that are looking at chemical dissolution methods, where basically instead of using limestone that you have to heat to emit carbon dioxide to get reactive lime, how do we use other mineral resources, perform a small amount of dissolution with things like acids, leach out the materials that we actually want without needing these high temperature processes. Next. So as we discuss these alternative materials, it's really important to put into context of, well, great, there's all of these new materials. How do I start to implement them? And what else do I need to be worried about if I'm going to make a switch? Because we want to make a change, we want to reduce emissions, but we also know that we want our highway systems to continue operating. So as we look at these alternative types of materials, what we need to take into context is there's a bunch of different types of alternatives. Like, we want them for our structures and services, and we want our structures and services to either perform just as well as they currently are, or maybe even better. If you click on that again, we need a fair bit of resources to produce our materials because we have a huge amount of materials that we consume, and we need energy to produce our materials. We also need energy to maintain our structures and services. So we're not assuming that we're going to put one of these materials in place and then wander off and it'll be totally fine, but we need to take into account that there's going to be certain maintenance regimes, and that's going to have a difference in terms of energy demands. On top of that, we need our structures and services to supply our energy resources. They don't just appear. We can't just plug our computer into an outlet and go, great. In fact, we actually need to generate our electricity, put it on a grid, get it to our wall in order to plug in our systems. And as we look at each of these different applications of materials, we also start to see that we have no perfectly efficient systems. We're always going to generate a bit of waste. Depending on the method that we're using, it could be more or less waste than what we're currently generating. We're going to have the production of greenhouse gas emissions, which is what we're focusing on today because we're discussing near zero and net zero materials. And we're also going to have the formation of air pollutants. That's going to be both from the materials generation themselves, so things like dust particles, as well as from our energy resources. So things like, again, particulate matter, SOx, NOx, etc. One more click. And then, of course, we also have water resources that we end up consuming. This is associated with things like the energy water nexus, like there's no way to get energy without using a little bit of water, and there's no way to get water without using a little bit of energy. And we also use water in the production of concrete. It's a constituent, but also as a dust suppressant, as well as a cooling agent in certain stages. And we know that there could be water contamination, especially if we switch to a material that leads to an accidental leachate. And we know that all of these aspects can potentially affect human health. So as we start to look at these alternatives, it's really important to pay attention to, well, let's make sure that we're actually quantifying the benefits associated with them. This is not something that the individual departments of transportation have to do, but rather looking at things like EPDs to make sure that we're understanding how this new alternative actually compares to the thing that we're familiar with, so that we know that we've selected something that's actually beneficial for our particular location. Next slide. Just as a pinch of context for that, this is a standard mixture that gets used actually a fair bit in benchmarking. It's reported on the NRMCA website as well, where we basically have consumption of different resources to produce concrete. And this is looking at weight fraction. So you've got your cement, you've got your interground limestone, you've got some fly ash, water, aggregates, etc. If we think about greenhouse gas emissions, the vast majority of our greenhouse gas emissions are coming from cement production. I already said this at the very beginning, and it's also kind of logical from the perspective of we have to produce cement, whereas we can quarry aggregates, there isn't quite as much impact. One more click. And now we see that if we look at another impact, in this case, I just pulled water consumption because it's a topic of discussion often in California. What we end up seeing is that, dissimilar from greenhouse gas emissions, cement isn't the only thing that's affecting, or the primary factor that's affecting, water consumption. In fact, because we use water throughout the supply chain, all of the constituents contribute to water consumption. And in fact, the water that we're using in batching isn't even a large fraction of the water that we're consuming to produce concrete. It's only like 10 to 15%, depending on your individual mixture. So having a sense of what impacts are of concern to your particular locality, and how are the different decisions going to lead to a change, not only in greenhouse gas emissions, but other impacts, could be of value. Next. So as we start to think about these different alternative materials, there are frameworks for implementation, and you can actually develop one that's unique to your Department of Transportation if that would be beneficial for your audience. Basically, what you want to do is first create a foundation of assessment. Make sure that you have the goals and measurable actions associated with what you're trying to assess. Obviously, we're trying to reduce greenhouse gas emissions. So that's probably one, is you're going to have a benchmarking associated with greenhouse gas emissions, as well as a goal for reduction. Maybe there's going to be an additional one of, look, we're in an area that keeps getting droughts. I also want to make sure I'm not consuming too much water. But maybe you're in an area with tons of water and it's not a big deal. You're going to also want to decide guiding principles at this stage, such as, I want to use life cycle assessments reported in environmental product declarations, and assess what unintended consequences are you most concerned about. So I'm going to have a concrete production facility in the middle of a downtown location. I'm really worried about particulate matter, for example. Then you're going to come up with decision-making rules. These can include things like preferring to reduce your greenhouse gas emissions associated with your individual systems. You're going to have a bunch of different alternatives that you can explore, and that's where you're going to start to look at your foundation for assessment. You might actually be engineering within materials that are already existing products. How do I compare across concrete mixtures that ready-mix producers are already trying to sell to me? Here, you could look at the targets that you've set, characterize any changes in performance. Maybe you can optimize your aggregate gradation, reduce a certain amount of paste demand, and then actually say, ooh, great, I lowered my greenhouse gas emissions. You also might be looking at some of these alternatives. So you might want to do things like define desired attributes. I'd really love it if this alternative cement can actually make it easier to have this material set quickly, as well as how can I make sure that I'm reducing my greenhouse gas emissions and still getting my desired performance. Then you're going to want to do comparisons across the alternatives that you have available to you, assess key parameters that are actually of importance to your group, which you have defined in your foundation for assessment. And that's your evaluation stage, where you say, did I reduce my greenhouse gas emissions? Are there any community needs that I didn't address or that I could address better, or that this alternative does a really fantastic job addressing? Are there economic feasibility or resource availability issues that I need to pay attention to? Like my location doesn't have a particular mineral resource, but it does have another, and that's going to affect the cost associated with importing one versus another. And of course, the technical performance. We should never be compromising on that. Then you could start to select and implement through these preferred alternatives. Next slide. When you're actually thinking about this for a Department of Transportation, keeping in mind that you want to stay technology agnostic, we want to look at all of the possible solutions and establish the understanding based on physical, thermodynamic, and environmental potential, right? So which resources actually could work for my particular location? Next, you want to make sure that you have those environmental impact assessments associated with the material. Did I actually lower greenhouse gas emissions compared to what I have available to myself? Conduct supply assessments to make sure you can actually get those resources. Determine that the technology readiness is actually appropriate, or maybe you need to pay attention to a couple of additional barriers. There has to be some degree of laboratory scale validation. Maybe your DOT has partnered with a university or has their own research lab. A fair bit of concrete testing to ensure that you have the appropriate strength and durability characteristics. Field testing to ensure that you have appropriate utilization of that material in the actual field applications and environmental conditions that you're interested in. And then any other steps that are individual to your particular Department of Transportation. Luckily, for a lot of these more novel materials, the first handful of steps, the folks who are making the materials are already going to have tackled. They're probably going to have tackled steps 1 through 4 because they're trying to get their new material on the market. But you might have a little bit of additional concrete testing or perhaps field testing in order to ensure that that is something that you could actually start to integrate into your DOT. And what we want you to be aware of is maybe we should start planning ahead for this. We know that our cement and concrete markets are starting to change in order to meet decarbonization goals. We know we have a lot of new startup companies that are trying to tackle some of these alternatives, and Ben is going to touch on those in a little bit more detail. And for your DOT to be ready to adopt those new technologies, having a framework of how to implement those and making sure you've got step by step, here's what we need to do, here are the check marks that we need to actually apply, could actually accelerate how quickly you can integrate those particular technologies into your specifications and your utilization. And if you are able to actually report and publish how you're going to do the checking of whether or not you're willing to use those materials, then the companies who are producing those materials can be aware of what you're going to check, and again, potentially help get some of that information out a little bit faster, again, accelerating how quickly you'd be able to do your testing. Next slide. An example of what's going on in California in this front, again, just because I'm from California, I'm not putting one state above another, it's just I'm in California. We work very closely with the University of California Pavement Research Center, and they have actually started to put together a structure to help Caltrans do exactly what we're discussing. Here's a whole bunch of alternative materials that Caltrans is getting bombarded with. How do they start to weed out the ones that won't work for California, pay attention to the ones that might actually be really beneficial, and start to test them at a rate that'll allow them to adopt them quickly? One of those methods is the Lab to Slab initiative that the UCPRC, the UC Pavement Research Center, is starting. Basically taking from those lab test results, those assessments of the individual materials, the compressive strength, et cetera, and actually putting them in a slab so that we know any constructability issues, any issues associated with longevity tied to that material in true environmental exposures, not accelerated lab conditions. So I have a QR code from our colleagues at the UCPRC shown on the screen, but I'm also happy to send that information later. But in case you want to see what Caltrans is doing to see if you can mirror it, that's where you can go to start to play around with that information. Next slide. Okay, I'll talk through a couple of fast wins kind of quickly because I feel like I've gone a little longer than I meant to. One way that you could start to reduce emissions quicker without having to start necessarily get all of these testing of brand new materials into your rubrics is to start to look at how we're actually specifying materials. One is tied to performance-based specifications, actually making sure that you're not relying exclusively on prescriptive design with specifying an exact amount of cement, but rather actually what performance do you need. Also, are there any ways that you can improve longevity? Can you repurpose any of your systems as opposed to knocking them out and completely replacing them? And in cases where you're using more than one material, making sure that you're actually designing for both materials to reduce greenhouse gas emissions. So the classic example in structural engineering is a concrete reinforced beam where maybe we could reduce a little bit of the steel that we're using and increase a little bit of the concrete, because steel actually has higher emissions than concrete, at least in California, and actually start to drive the whole beam design into reduced emissions by paying attention to the multiple materials that are getting leveraged. And then, of course, paying attention to things like when you have somebody who's going to be putting a bid on your roadway system, they're going to be a little bit risk averse. They're not going to want to let you down. So if you have any type of insurance that you can offer in case of risk of failure, for example, you're only going to be placing it in sites where there is low risk of failure, or you're going to not hold the contractor accountable for certain types of failures because it's a novel material, that can also start to encourage contractors to start to explore these alternative materials. I think the next one's our last slide. Yeah, so this is a very, ivory tower, how to think about this big picture diagram that I just threw in here for a wee bit of context, but I won't spend too much time on it. As we're thinking about how we use our materials, we want to think about them in terms of how we can use them most efficiently. And that's what a material use hierarchy allows us to do. So in general, we would love to reduce the amount of material that we actually need. So if we can design our mixtures a little bit more efficiently, we would love to reuse our materials if we can't reduce. So that would be like repurposing something as opposed to replacing it. If we can't reuse it anymore, can we recycle any of those resources? Are we able to use that crushed concrete as road base in our system? If we can't recycle for whatever reason, is there any other way that we can recover some of the materials from that system? And if we can't recover, that's when we dispose, only when we've exhausted all of our other options. So with that, I will pass the baton over to Ben.
Thank you, Sabbie. Appreciate that great introduction here. My name is Ben, and I'm a manager on RMI's cement and concrete team, which sits within Climate Aligned Industries. Going to provide a little more context today into the cement and concrete innovation landscape, and in particular, talk about a few of the exciting startups and players that are getting involved in the space. To start things off, there's a lot of momentum towards decarbonization of the cement and concrete industry. We're not only seeing industry commitments and efforts from GCCA and NEU, as well as individual cement companies, but we're also starting to see the emergence of demand-side signals through First Movers Coalition, Buy Clean provisions by GSA, and of course, broad calls from a variety of NGOs and academia for movement towards decarbonization actions. Now, there's a lot of different ways that decarbonization can ultimately be achieved, or levers that can be pulled. At RMI, we certainly believe that it takes an all-hands-on-deck approach to decarbonize cement and concrete. Carbon capture, of course, is one potential option, but that is a very expensive and energy-intensive one. And so there's going to be a lot of other things that happen before we entirely rely on carbon capture. And so SCMs are one great way to reduce the embodied carbon of cement blends. Of course, traditional SCMs are already used, type 1L cement being a more common blend that we're seeing these days, as well as use of slag and fly ash. But in the future, we expect a reduction in terms of availability, particularly on slag and fly ash as other industries decarbonize, resulting in the need for new SCMs. In addition to that, we do expect a great uptick in demand for SCMs in general. And so there will need to be new materials that come and fill that. And so what are alternative SCMs? Well, they're SCMs that are used as substitutes to help lower the amount of carbon-intensive clinker that is used, and also in some cases improve performance, as Sabbie had mentioned here. And why do we care? These SCMs, again, can help increase the amount of cement replacement and therefore lower the amount of emissions that are in the mix. In addition to these alternative SCMs, we also have alternative cements, which are beginning to emerge in the space. As I mentioned, decarbonizing OPC does require CCUS, which is very expensive and also can be logistically challenging for a variety of different site locations. My team has worked closely with a few different cement producers and trying to think about how to actually move around CO2 to the storage sequestration sites is a big challenge. And so alternative cements are beginning to emerge as perhaps an alternative. Alternative cements do leverage material and production process changes that can result in different properties on a physical and chemical perspective, but they often are combined with lower carbon emissions. And again, they do offer a different pathway to net zero, and we do expect the growth of these in the coming years. To mention a few that Sabbie had already kind of touched on here, on the alternative SCM space, we see the increase of calcined clays, LC3 cement being a very common one. that is being cited and growing in the US and globally. The opportunity for concrete fines, reactive silica, newer synthetic fly ash, slag, or limestone. There's carbonated SCMs, as well as bioash. On the alternative cement side of things, we see Belite-rich cements, calcium sulfoaluminates, which are already in use today, as well as the increase of alkali-activated materials. Potential for bio-based cements, calcium silicate-based cements, such as what we're seeing from Brimstone and Sublime, and carbonation-based cements. I mentioned a few companies here, but there is a lot happening in the startup landscape. And so we've broken it down into 3 buckets, more or less here: make less, make better, and make new. In the make less space, this is the increase in use of SCMs. And so as we mentioned, there are a lot of different companies who are starting to explore how can we tap into new supplies of SCMs. To call out one, I'll mention Forterra, who is actually producing Vaterite at their plant in Reading, which recently opened. They're making a recarbonated blend that can then be used as an SCM. They're also on the make new side of things because they're pushing towards full replacement as well, but in the interim are just pushing on the SCM front. In the make better, we have optimization solutions. These often will allow for greater uptake of SCMs and alternative cements. And so whether that's more precise mix specifications, which companies like Alchemy are doing at the ready mix truck to provide better readings and on-site opportunities for measurements, or Blue Planet, which manufactures aggregates that also sequester CO2 and allow for cement reductions. Lastly, on the make new side of things, a lot of really exciting emerging cement blends. Brimstone and Sublime are just 2 that I'll mention here, who have recently gotten DOE funding to actually push forward their plants. So the DOE funding that recently came out through the Industrial Demonstrations Grant provided substantial amount of CapEx for a variety of different cement decarbonization projects. I think it's really interesting to note that of the 6 total projects, 5 of them include some sort of new or alternative cement blend. And so, of course, with Sublime and Brimstone, this is a alternative cement entirely. And then 3 of the projects incorporate calcined clays and LC3 cement in some way, shape, or form. And so this is certainly something that we see is coming and it's emerging. And so I want to make sure that both DOTs and private producers as well are ready. To speak to some of the benefits that Sabbie already mentioned on the SCMs front, it's really important to note that while there often is some compromises as far as early strength or differences in workability, there are a lot of benefits to using SCMs in addition to the carbon reductions. For example, natural pozzolans have great durability and increased resistance to chemically aggressive environments. Similarly, calcined clays also have really good strength and durability benefits and are perform really well in environments that have sulfates. Vegetable ashes are another emerging SCM that can show improved long-term strength and durability. And lastly, I'll mention concrete fines, which has that great circularity aspect that helps reduce landfilling of demolished structures. And while a lot of these technologies and different SCMs are newer, there still are examples that exist of their use already. And so LC3, for example, in the top left here, we have a model house in India that is made of 98% LC3. Below it is the Swiss Embassy building in Delhi, which is built with LC3 prefab materials. Have a photograph of some of those LC3 prefab blocks on the top right here. And lastly, I also wanted to highlight in the bottom right, there are LC3 pavements that are being used at UCLV in Cuba. Expecting growing projects to pop up here in the US as well, especially as we see the growth of those calcined clay DOE funding opportunities. Sabbie did mention this earlier as well, but the emission savings potential of alternative cements, it does vary based on the type of technology that you're using here. And so Belite-rich cements and calcium sulfoaluminates, which already do have some use cases, on average reduce the embodied carbon by around 10 to 30%. Alkali-activated materials can reduce by 40%, or even beyond that in some cases. Then we are seeing the emergence of some net zero cements, particularly calcium silicates. We're not showing bio-based cements in this because there's not as much publicly available data, but there are others in addition to calcium silicates that are pushing towards that net zero cement opportunities. I started to touch on a few of the challenges here, and do just want to note that, again, these are different materials and they will take time to work with. We're seeing a bit of a two approaches as far as integrating with existing cement operations versus disruption. Both have their pros and cons here, but really what it comes down to is needing to be able to source raw materials at scale, try to be cost competitive with OPC. We mentioned how expensive carbon capture is, nearly more or less doubling the price of cement. And so that's another comparison to think of actually from the dollars per ton of CO2 abated perspective, how this fits in. A lot of challenges on the standards and codes acceptance side of things. It is worth noting that some of these new cement blends, such as Sublime, is actually already certified under ASTM C1157, whereas Brimstone is certified under ASTM C150. And so reaching those ASTM certifications is one part of things, but of course needing to ultimately get onto the approved materials list of DOTs is another. Testing for standards and performance requirements and the increase in EPDs is really critical here. It's challenging to move through the EPD process when you are a startup, as they often require 18 months of data at commercial scale manufacturing facilities, which most startups don't have. And lastly, of course, consumer preference and risk aversion is something that we do see in the market. This does give DOTs the opportunity to help de-risk innovations for the rest of the construction industry by pushing forward testing and pilots. I did quickly want to mention that the Decarbonized Cement and Concrete Alliance exists. This is a group of innovators in the space who are facing these common challenges and problems and are working together to try to unblock them. Would be very happy to facilitate any connections to DOTs who are interested in working with these companies or exploring some of the challenges and solutions in the space here. So lastly, just wanted to provide some recommended project opportunities, and this comes from a publication that RMI put out earlier this year. But we do want to encourage the development of concrete mixture approval processes that is performance-based and also applicable to all concrete materials. As we mentioned, the site demonstration placements to evaluate the constructability and performance of these low carbon solutions is critical to get more data out there and more comfort amongst construction workers to actually become used to using these materials. We do want to set informed near zero or zero global warming potential thresholds without being too prescriptive as far as materials. This allows for greater flexibility for local needs. Leverage EPD procurement processes to ensure that low carbon outcomes are validated is critical as EPDs are starting to become more commonplace in the US. And lastly, of course, coordinate amongst DOTs and FHWA to develop consistent data framework across the states and just really collaborate as much as possible so that these solutions come into the forefront. I'll conclude with sharing this QR code, which has RMI's recommendations for how to move towards low carbon concrete for FHWA, LCTM applications, and hope you explore this in more depth. We're again happy to have any follow-up conversations. Thank you for your time, and I think we'll move into Q&A now.
Thanks, Ben. Thanks, Sabbie, for those great presentations. There's a couple of questions that I think we can surface now. One that was brought up earlier was just a question about, Portland cement manufacturing in general and how that fits into this concept of near zero emissions concrete and cement. And, from these presentations, we've seen that essentially there's two ways to look at it. There's decarbonizing those existing facilities, which make OPC, and that's very challenging, and you'll need to incorporate some amount of carbon capture and storage. And then really what we've been emphasizing in this presentation is all of the alternatives that are out there, whether they're SCMs or emerging alternative cements. So I think the goal here and the idea for infrastructure builders is to get going with testing these new materials so that you're ready for applying them in larger scale projects over time. And that last slide that Ben presented, which with the QR code, which we can drop a link to, is a resource we put out for DOTs to guide them with their grant applications for the FHWA low carbon transportation material program, which you can use those funds to try some of these things. And we've already heard of DOTs out there that are doing projects similar to Lab to Slab, which Sabbie covered in others. So, and really encourage DOTs to go after that funding for these types of applications. Another question that we got was from Sandy Doyle, who says, has the value of additional benefits of SCMs been quantified in any way? So potentially beyond just the carbon reduction benefits. I guess I'll pass it to Sabbie first if you have any reflections on that.
Yeah, are we thinking like performance benefits? Are we thinking other environmental impacts? What are we thinking in terms of quantification? Because the answer is yes, but I also don't know what information to discuss in more detail.
I think performance would be interesting since
yeah,
that's a concern. Yep.
Yeah. So you're now going to see that my background's a little bit more in structural than in pavement design. But a lot of our supplementary cementitious materials actually improve many of the durability characteristics that we're oftentimes concerned about when we stick steel into our concrete. So they will drop the pH of the overall gel that you have in the system, not by too much, but like by a wee bit. But a lot of our pozzolanic reactions that we get out of a huge chunk of the SCMs that we use regularly actually improve the pore structure within your system. Basically, it creates like a little bit of a densification, and that then reduces permeability, starts to reduce a lot of our other durability concerns that we see within our systems. It also could help if you have like silica-rich aggregates. Oftentimes we'll see improvements in things of like alkali silica reaction. We could see improvements in terms of a bunch of different types of shrinkage mechanisms because you're basically going to start to reduce a lot of the chemical shrinkage drivers. So there's a lot of potential improvements if you get a nice reactive SCM.
I'll add to that too, that SCMs are really one of the most cost-effective ways to help reduce embodied carbon in the cement and concrete space. In many cases, we actually see that cost savings upwards of $25 per ton of CO2 abated can occur. Of course, there are CapEx expenditures that need to happen as far as additional grinding or storage silos, or in the case of production of calcined clays, the actual calcination unit or retrofit. But those cost savings over the long run can actually provide for a profitable way to help to move towards decarbonization here. And so SCMs have good performance characteristics. They help decarbonize and also can help reduce costs. So they really are a great solution here, and one that can be deployed in the short term.
Great. And one more question before we can move into the live polling. So folks have been talking about advanced market commitments. The First Movers Coalition and the US DOE liftoff report both had that as a recommended strategy. Can DOTs do those kinds of forward purchase contracts? I guess I'll pass it to Sabbie first, and I have some reflections as well, which I can come back to.
I mean, I feel like that's actually almost like a bureaucratic question of like how the individual DOT is structured. I fear I don't know the answer to that. I know that the startup groups who are trying to get those advanced market commitments would love it if a DOT would say, you know, here's a market commitment. But I think it's going to be a little bit specific to how an individual DOT is actually run, or even, you know, like a local city or county municipality, because they also manage a fair number of roads and highways as well. So I fear I don't know the answer to that, but it'd be wonderful. I'll pass it back to you, Anish.
No, agreed. It's sort of a gray area right now. I think that the short answer is there's not really, especially for cement, because DOTs don't buy cement. They're contracting for projects. So it is an area that folks are exploring right now, and a number of DOTs are interested in this and just sort of working through the logistics of how an advanced market commitment could actually work. Yep. So no great answers there. Okay, I think there is another question about carbon star ratings for low carbon concrete procurement, which we can answer via text unless, Sabbie or Ben, you're familiar with the carbon star rating program. Are you familiar with that? It's like sort of another way to qualify environmental claims.
Yeah, I could plop a link in for it, but it's just another way to compare. Yeah.
Great. Okay. With that, I'll share my screen, and we would love to get the audience to participate in this next portion for as we close up in the next 10 minutes. And just screen ready. So on the screen now, you should be a QR code and then also a web link to menti.com. So this is just a quick live polling tool that we use to get a sense of where the audience sits with some of this information and hear a sample from you all. So you use a QR code or the web link, you can just type in menti.com, and then there's this code that's here, which will get you into the questions that we're going to look at together for the next few minutes. And they're very simple questions, so it's not a quiz. And the code will be on each slide as well. So I'll just move forward to the first question in the interest of time. All right. So coming into this webinar, our first question was like, what is your knowledge of near zero emissions concrete products? Haven't heard about it, or have heard about it, but don't know any specific things. Have heard about it and I'm interested in trying specific technologies. So maybe you started to explore, some of the specific strategies. And have you had conversations with specific technology vendors? Are you like at a stage where you've gotten, testing reports, lab reports from these vendors? Great. It looks like people are coming in across the board here. Very promising that a number of folks have had conversations with specific technology vendors. And at the top of the screen, again, is the information if you are still struggling to log on. And if you have any questions on that, use the Q&A function and folks will guide you to get on this live poll. So I think the responses are slowing down. Seems like most folks are still, learning about this and, could use help getting towards this next step of having specific conversations to pilot technologies. Great. Next question. What do you believe is your first step to demonstrating near zero emissions concrete? So you can check multiple here, but I'll read out the responses since the text might be small. So first is engage state DOT leadership. So do you need sort of top-down direction to get going on this? Do you want more education, discussions with other DOTs, other infrastructure agencies, partner on testing and validation of these mixes, and using performance-based specifications or performance engineered mix design to demonstrate these technologies? So I'll give folks a few to respond. Looks like most folks are saying the way to move forward with this is with performance-based specifications or a performance engineered mix design. We wholeheartedly agree with that. And again, partnering with other DOTs as well. I think maybe Sabbie mentioned this, but publishing, if you're a DOT and you demonstrate one of these products, publishing the results from your testing would do wonders for just general confidence and market acceptance of those materials, and then also for the vendors themselves to learn kind of how that feedback loop. So partnering with other DOTs to learn more. Okay, this is just a fill in the blank. If you said other, if there's something else as a first step that you wanted to surface to the group, maybe it's not just about performance-based specifications or testing and validation. Is there something else? Feel free to fill in the blank here. Just type in a response. The fill in the blank ones typically get a lower response. I understand. We're asking you for more here. But if you have any other ideas, we would love to hear them. So I'll just pause for a moment. No great ideas. Incentives, okay, that's great. Yeah, the cost piece is a real one. And it may not even be a financial incentive. It could be some type of administrative or bureaucratic incentive too. Great. well, feel free to continue to respond to that one if you're still populating that blank space, and we'll move on to the next one. So reflecting on that earlier question about what's the first next step, we really wanted to get specific here and say, are you interested in or are currently pursuing a demonstration project using performance-based specifications? Looks like everyone is all in. Oh, spoke too soon. Someone is not interested in this. Just give it a moment for more folks to respond. But this is very, very promising. And again, I will plug, if you are a DOT, you still have 10 more days to apply to the FHWA LCTM program and could use that funding to demonstrate projects with performance-based specs. So great, 19-1 performance-based specifications are the way forward. And getting even more specific here, performance-based specifications could apply to a broad range of materials, but really what we're asking here is, are you interested in demonstrating these near zero emissions concrete products, the alternative SCMs, alternative cements, using this methodology of performance-based specification? Great. Awesome. Well, clear response there for those last two questions. If you want to learn more about performance-based specifications, there are a number of resources online. We can point you to our previous webinar as well, which covered this topic. It had some good highlights from Canada's experience developing performance-based specifications for concrete. All right, I think the next one might be our last. And this is just a broad question, another fill in the blank, but what type of support, education, or technical assistance do you need to begin using near zero emissions concrete products? So could be just more transparent lab data on the performance of the products. It could be that same data, but on the environmental impact side of things. Could be more sessions like this, more discussion. That's very interesting. Could use help dealing with insurance companies to see how they will treat our use of these new materials and get their support. More case studies. Understand impacts on design and construction practices, more training. These are all really good suggestions and also involve more stakeholders. So, bringing more contractors and engineers, design engineers into the discussion, insurance as well, contracting, cost versus benefits reporting regarding carbon intensity. Well, great. Thanks everyone for your participation there. We can, share these results. If you're still putting information in, please finish that up, and then we'll share this with our recording and slides later. And I think we're at time. So again, another huge thank you to our speakers, Sabbie and Ben, for those great presentations. And we'll share what we can from the slides as a follow-up to this meeting. And if you have any additional questions, don't hesitate to reach out to the RMI team, and we'll be able to put you in touch with Sabbie or others who were referenced in the slides. So thanks everyone, and have a great rest of your day.